Well, hello. So today I'd like to talk about perfect form, variational principles, methods, and applications in elementary physics by Don S. Lemons. I thought I was going to have to do a couple of books by Don Lemons. I like a lot of the books by Don Lemons. I've got three only, but I like them all. And I've used them extensively in classes, especially when I taught at the SLAC, at the small liberal arts college place. These are really nice books. He has a really good way of describing things, and he's nice and concise. So, this is a book on variational principles in physics. Variational principles are what physicists like to think of when they think of mechanics. They don't really go to Newton's laws all that very much. Well, I guess they do, but you need to know a lot about these things for later uh, applications. But this is short. It's only 114 pages. Now, this is basically like the second half, let's say, of your mechanics class, your junior mechanics class. The first half being going over Newton's laws again, going over Newtonian mechanics again, this time in a little more depth than you got in your introductory physics class. But the second part is coming here and really using all that good differential equations stuff that you learned in differential equations class or possibly a math methods class. So perfect form, very nice book. And it really goes through just the basics, right? So I don't know if you know this, but if you were going to go do some quantum mechanics, let's say you wanted to learn quantum mechanics. Quantum mechanics is all explained in terms of these variational principles, in terms of a Hamiltonian method. So you have a Hamiltonian method that describes how the wave function evolves. That's what Schrodinger's equation is basically doing. So this is very important for going on to later parts of physics, the more advanced physics. You have to really get this down. So this particular book, it's short and it's for the subject fairly simple. So I think this is a really good book for someone who wants to go through variational principles by themselves, either because they're a self-learner, or because they want to get a little more practice with variational principles, either before their quantum mechanics class or more likely before they go to graduate school. So nice and short. That's helpful. I think it has, I'm going to guess, 7, maybe 8 chapters. 7 chapters. All right. It just talks about different variational principles. Chapter 1, here is the principle of least time. This is going to be very important for understanding optics, basically. So this is the reason why you have Snell's law and stuff like that, is this principle of least time. A light ray going from one spot to another, and there's, say, air here and glass here, is going to refract based on how fast it's going on either side. And what light wants to do is it wants to get there as fast as possible. So it's going to spend more time in the medium with the lower index of refraction because it moves faster there. And that's basically the principle of least time. And in here, you have Hero's problem. That's very important. But in here, he goes through and he talks about these different, Fermat's principle, the principle of least time. He talks about image formation and stuff like that. Part 2, he goes into calculus of variations and talks about the Euler-Lagrange equations. Very important, and they're going to be used over and over and over in the latter part of the book. Basically, this is a way to figure out some minimizations. Right? You've got I should have practiced brachistochrone. I did it. I actually said it correctly, right? So the Christochrone problem, and I can't do it when I don't have the word in front of me. Let's see if I can see it is basically the least time, right? The path of least time. So this is under gravity, right? So this is a problem 2.2 here, and what you're going to do is you're going to find the shape of this curve that gives you the least time here. At an AAPT meeting, American Association of Physics Teachers meeting, a few months ago, I heard a really nice talk about brachistochrone problems in introductory physics. But those are just sort of the qualitative analysis to try to understand if you can apply the basic principles of Newtonian physics to explain some of the rationale behind this. Why does it work, right? This also has a very interesting property that if you start at any point along the brachistochrone line, let's go back there. If you start here from rest and fall down here, and start here from rest and fall down here, it's going to take the same amount of time. And so that's basically what he was talking about is, can you explain that just using, qualitatively explain that just using Newtonian mechanics? And you should be able to, but it turns out that it's very difficult for students, both freshmen and juniors, and a little bit for graduate students. Curved light is going to take these two and put them together. And now, rather than taking straight line segments in chapter 1, you're going to use this ability to find these curves. I just said we had this least time curve for a falling particle, and we look at that now in variable index of refraction material. The book all about that, which is much more complicated, called Geometry and Light. But let's just look at this one. This is page 35. It gives you the mirage, right? So this is the explanation of the mirage, which is, even though this straight line is the smallest distance, the smallest time is this curved line, because here, near the surface of something hot, let's say like a road, the index of refraction you heat up the air, you get a lower index of refraction, so you get a bend basically in the light ray, and that bend in the light ray is what shows up to your eye. That other book, again, it's within range here, Geometry and Light, the Science of Invisibility, that actually goes into all the differential geometry and stuff like that, that you don't need to really know about. You'll notice here that you have a few more problems. You had 5 in chapter 1, 5 in chapter 2. You go to 10 in chapter 3. That's okay. This is still a lot fewer problems than in a standard text. I worked fouls, for example, over the summer, two or 3 years ago, probably 2 years ago. And it just has way too many problems. So I worked all those problems, man. Oh, well, got about half of them, I guess. But it's still a lot of problems. And if you don't know the stuff already, if you haven't been through it already, you don't really know when to stop and go on to the next section, right? You say, okay, I've done enough of this, I know it, right? Because you don't know what's going on. Chapter 4, we get to the problems of least potential energy. This is little more advanced version of what you did in introductory physics in Physics 1. You'll notice here we get constraints and Lagrange multipliers. This is something that you get in your junior level physics class as well. Technically, you see it in Calculus 3. You're supposed to see it in Calculus 3, but I know I was completely surprised, in my senior year of college when I opened up my old calculus book and I saw the Lagrange multipliers. I didn't remember them at all. They just happened to be in the back of the calculus book. So I'm not sure how much time you actually spend on that in Calculus 3. That is the biggest problem with one of those huge books, is that you just go through in the, or I guess in a survey class, you just topic. You don't have time to actually think about what's going on. So here we have some other things like the catenary. That's another important problem. 55 over here. In that case, you've got what is the shape. Oh, it doesn't have the drawing. Oh, I thought it would have the drawing. I thought I saw the drawing, to be honest. I guess I just imagined I saw the drawing. So the catenary is the shape where if you hold two ends of a rope, what shape will that rope have as it hangs down if it's a loose rope, if it's not taut. So that's an interesting one that you need variations to do. Chapters 5, 6, and 7 are really, really important, though. Right. So here we end up with least action. This is basically the Lagrangian. Actually, I think get the Lagrangian in here. This is working up to the Lagrangian, I guess. The principle of least action, and this is one of the three ways to build mechanics. So basically, chapter 5, 6, and 7 are principle of least action, the Lagrangian, and the Hamiltonian. The Lagrangian is, the most fun one. Sometimes they now give descriptions of it as in general relativity. If you want to use general relativity in some more modern formulations, you have to understand the Lagrangian formulation. Right, so when I took general relativity in like 1995 or whatever, it was all just tensors and stuff. But now we've got things like variational approaches to gravity field theories, and this is all, there's my notes. This is all just Lagrangians and stuff like that. So you have to have this going in even to Einstein stuff. That wasn't so much true as far as I know. I mean, I was just taking a class. I didn't do any research in it when I was younger. But as far as I can tell, that's a little bit later. They did, even though they may have had some ways to do it, it wasn't really, really important until fairly recently. Probably after you were born, but still comparatively recently. Interesting things here like generalized Kepler's third law and stuff like that. So the actual orbits, ball within a circle. I'm going to go through some of these problems in a second because a lot of them are some of my favorites. And then Hamilton's principle extended. That's going to give you your Hamiltonian. Generalized coordinates and all the horrible things that you're going to hate if you have not taken your junior level mechanics class yet. So let's look at some of these things. I do want to get to the Watts governor. That's fun. So let's just go through and look at some of these problems. Hero's problem, that's basically reflections. Then we have here some stuff with Snell's Law and stuff like that. Here's an interesting one on least resistance. So you can do that. So all very simple little problems there. I shouldn't say simple, but they take a little bit of work, but they're things you can think about and things that are fairly standard, not too horrible. Here he's just asking you in the Euler-Lagrange equation just to take this particular functional form and figure out the shape. Then the Brachistochrone problem, all doable. This is technically doable with if you could build your differential equations out of Newtonian mechanics, because I did that about 6 months ago. I was talking to that guy at the APT meeting. I did that, so it's something you can do. I would not suggest it, though. I would suggest figuring out how to do it this way if you want to learn how to do at least. These smallest path sort of things, least whatever path, minimal paths. Curved light stuff. Let's see, which ones do they have? Atmospheric light trajectories. So, in here what he's done is he's giving you certain functions for the index of refraction and said, okay, take these, and try to figure out what's going on for the different indices of refraction. So designer rays, you're given a path and you're supposed to find a index of refraction. This you're given index of refraction, you're supposed to find a path. Falling light, take a more realistic index of refraction, find the path, that sort of stuff. So very nice. Least potential energy, hydrostatic balance, stuff like that. Things that are important. Loaded column with stretching and no stretching, stuff like this. Occasionally you see that, a lot of these actually, you occasionally see in the end of the problem lists in your Physics 1 texts. And a lot of them can be done, like this differential stretching of a massive slinky can be done with elementary mechanics, with just Newtonian mechanics. It requires some thought. It requires you to be either very creative or very organized. Okay, either one of those will usually do. So I'm trying to think of which is the one that I've seen. So this might not be right for this one, but there's the chain falling on a table problem, right? And I don't recall exactly what you're supposed to find with that. But when I got the solution to that, it's sitting there. It's in at least one of my junior level mechanics classes as an average sort of problem. It's in Survey as one of the challenge problems, and so I did that, right, myself, using a very restricted set of principles from Physics 1 and just did it very, very precisely, and it works. I didn't have to do anything that required any real insight or anything. I didn't need any, eureka moment to do it. But then I looked on YouTube. Actually, I saw somebody else's solution, a student solution of the problem, and said, I don't quite buy it, right? Because it did require some real insight of what is happening with differential equations. So a lot of times you'll see, questions like this one, and the one I was looking at was, of course, the falling rope, that require some eureka moment, right? That require something out of the blue. And if you understand this factoid, if you can see this little factoid clearly without without having to go through everything step by step, you can solve the problem. But usually they're solvable by just a standard approach. So here we've got potential energies, loaded flywheels. Those are important. Obviously, flywheels are important. Cantilevers and stuff like that. Different kinds of energy. It's important to understand energy is different. I do not know. Oh, you don't know this one. All right. And here, yeah, the maximal land in a sea. All right. So loaded beams, again, here this is something that would be really hard to do without differential equations, without variational principles. But it's very important, loaded cantilevers, right? This beam here, this cantilever. Had a friend who was doing stuff with piezoelectric materials for she was designing piezoelectric materials for the gyroscopes, like the gyroscopes in your cell phone that tell it what orientation you have it in. And she required doing stuff like that. Minimum action, spherical pendulum, that's good. Orbital shapes, those are both good. These are things that are a little beyond physics 1, but are right up in here. And you can find these kinds of things that'll tell you, what the shape of your orbit is for a given energy. Different ways that your spherical pendulum can move around. Hamilton's principle, your Euler-Lagrange equations, your Lagrangian, very important. Spherical pendulum again, but this time as a, This time as a section, not as a problem. Kepler's third law, other fun things, optical Lagrangian redux, so you're supposed to redo the Snells Law things now with more advanced stuff. So good sorts of problems. So you have circles with masses. These are the kinds of problems that... A lot of the problems are unfortunately not really realistic. They're pedantic, right? But you're learning, so you want pedantic things, right? That's why it's pedantry. This particular problem is actually one of my favorites. So this is another one that's solvable. You can use, if you understand rolling motion, you can do this particular problem, a ball rolling in a sphere, just oscillating, or maybe a circle of tube, just oscillating back and forth in that cylinder. But it's one of these things that you have to be really careful about. And if you get the constraints right with your Lagrangian, it's easy. If you try to do it with Newtonian mechanics, you have to put in a lot of knowledge about each little thing that's going on there. It's not really horrible, right? That knowledge is right. What is the relationship between angular frequency or angular speed and speed here, and same thing for the rolling motion and stuff like that. So it's stuff you can do, but you have to be really careful. Hamilton's principle extended, and this is the end of it. I wanted to talk about Watt's generator. This governor, this is also an interesting one. So you see this a lot also in Physics 1, and it's rotations. What I didn't know, and I mean it's been a long time since I looked at this, but I didn't even think about it when I read this, I don't know, let's say 10 years ago. I'm not sure if it's 10 years ago or 8 years ago or what, but let's see, when did this come out? $1997. That doesn't help me at all. But basically, this is this rotating bead. It turns out that Watt, the same Watt, right? James Watt. He used something like this as a governor for the steam engine, right? To make sure that, the right amount of steam was coming out. So if the engine started going faster, this thing would raise, right? This will rise, excuse me, and that would reduce the amount of steam coming out, which would slow this down, and so forth and so on. So this was actually used as a governor. So we see this a lot in Physics 1 textbooks, because it's got some really interesting things that you can do with Newtonian mechanics, but you never actually get the backstory. So this is really nice. It has the backstory for Watt's governor, which isn't called Watt's governor in that system. Now here we have the sliding ladder as well, right? Another perennial favorite. So you see a lot of these same things that you see. This guy's also in those Physics 1 books, but you're going through them with the more advanced mathematics. And here's one that you probably do not see. You probably do not see the double pendulum in your Physics 1 book. But that's also very interesting. And now I want to do problem 7.8, ellipsoid of revolution. I love ellipsoids of revolution. Very important in magnetism, ellipsoids of revolution. So again, I really like this book. I think it has a lot of things that are useful pedagogically. And I think that if you want to learn variational principles, it would be very useful for you. I expect especially if you have a really strong background in your Physics 1 stuff. So, so I think, like a lot of these things, I think it's good either as a refresher for your junior level mechanics class, or as a supplement. So like I said, the text is really nice, and it really explains what's going on. So this is a really well written book. So it's a lot easier to understand than a lot of textbooks, I'll say that. So I think it might be useful as a supplement. I never know, since I didn't do this as a self-taught thing, but I think that if you are really good with the physics in your freshman physics sequence, then you could probably use this to learn your advanced physics, okay, your junior level physics variational principles. But I'm not sure what your process is, where you want to go with stuff like that. So again, I recommend this. I recommend this the same way I recommend a couple of the other books that I've looked at. Variational principles, some of my favorites. Although I don't see all my variational principles books, I'm a little lost. I don't remember where I put them. They're probably behind those other books. Okay. I have 2 rows of books, but I do see one on Introduction to the Calculus of Variation, so they're probably behind that one. Variational principles, again, very important. They show up in quantum mechanics and quantum field theory. I mean, the path integral is basically a Lagrangian method. Like I said, they show up in general relativity now, and they show up in statistical mechanics. We did a few in my statistical mechanics class when I was a graduate student. Problems with variational methods as well. So this is a very good introduction. I think you'd probably enjoy it. I especially think you'd enjoy it more than your standard textbook. All right. Then I will see you next week. Bye now.